Hey everyone, how's it going? So in this video, I'll be implementing some baseline application of BERT. Specifically, I'm going to cover question answering and next sentence prediction, and also masked language modeling. And it mostly will be about the code implementation and with the relevant explanation. Let's start. First, a quick word on the architecture of BERT. So, BERT is bidirectional transformer pre-trained using a combination of masked language modeling and next sentence prediction. The core part of BERT is the stacked bidirectional encoders from the transformer model, but during pre-training, a masked language modeling and a next sentence prediction head are added onto BERT. So when I say head, I mean that a few extra layers are added onto BERT that can be used to generate a specific output. The raw output of BERT is the output from the stacked bidirectional encoders. And the first step in my case would be tokenization for BERT models. So I am already in my Google Colab. I need to import BERT tokenizer. And then I need to let's define a random text as this, and then I'm going to do the get my encoding actually. Tokenizer dot encode plus. I'm going to use plus, and I'll tell you in a second what this encode plus is doing. The first parameter would be text. That is this one. 2022 would be a great year for all of us. Then add spatial token. Set it to true. I'm also going to set my truncation true, padding equal to max length. Oh, no, actually. That also, I'm setting it to true. And return tensor, I'm going to use PyTorch, so PT. Let's run this cell. Okay, this cell actually ran successfully. Let's print out this encoding. All right, so that's the tensor that I got after printing these encoded output. That is after this encoding actually represent the tokenized text, and this is my text. Now about these parameters, the first one, I'm setting padding equal to max length, which will mean that the padding argument actually controls the padding of the tokenized form. So it's padded by zeros to make all the text to the length of the max length. So it will pad to the length specified by the max length argument, or in this case, I have not specified separately a max length argument to be a number. That is my max length. I could have defined another parameter here where I will pass an integer for the max length. Here I have not specified that. So in this case, the padding will work like this, that it will pad up to the maximum length accepted by the model. That is whatever model you are using in your case. Also, I am using encode plus here instead of encode. And the encode plus specifically returns a dictionary of values instead of just a list of values, because tokenizer.encode plus can return many different types of information like the attention mask and the token type IDs. Everything is returned in a dictionary format, and if you want to retrieve the specific parts of the encoding, you can do something like this. Let's do the next steps actually. So in this case, what I'm going to do is that I want to retrieve the specific part of the encoding. So encoding, encoding, and attention mask. You can actually print this variable. Yeah, so all these zeros are because I have used padding equal to max length. That is, it is taking the maximum length accepted by the model and padding it all with 0 after my initial tokenized form. And another quick thing to note about the tokenizer is that you can specify to retrieve specific tokens if desired. For example, if you are doing masked language modeling and you want to insert a mask at a location for your model to decode, then you can simply retrieve the mask token like this. So you do tokenizer.mask token. Let's run this cell and I get this output mask. All right, now I am going to talk about the masked language modeling a little bit and then write the code. So masked language modeling is a way to perform word prediction that was originally hidden intentionally in a sentence. In simple terms, it is the task of filling in the blanks. And masked language modeling can be considered similar to auto-encoding modeling, which works based on constructing outcomes from unarranged or corrupted input. Let's start the actual coding. Some of the standard imports at the very first step. And then, yeah, I am going to actually use the same line. That is, my tokenizer will be just this, BERT tokenizer dot from pre-trained BERT base uncased. And my model will be this, BERT for masked LLM dot from pre-trained BERT based uncased return dict equal to true. And we have already imported this model from here in this line from transformer. So the masked language modeling works by inserting a mask token at the desired position, just like I was telling, where you want to predict the best candidate word that would go in that position. And you can simply insert the mask token by concatenating it at the desired position. The BERT model for masked language modeling predicts the best word or best token in its vocabulary that would replace that word. The logits are the output of the BERT model before a softmax activation function, which is applied to the output of BERT. That is, logits are the prediction scores of the language modeling head. That is, scores for each vocabulary token before softmax. And in order to get the logits, we have to specify return dict equal to true, which is what I have done here. In the parameters where you are invoking this BERT for masked LM, and so otherwise if you do not do this, you will get a compilation error. And return dict, actually by setting it to true, the model will return a model output class instead of a plain tuple. And you can check Hugging Face the official documentation for knowing what model output is all about. So yeah, so now my next line of code will be text equal to so what I'm going to do, this is masked language modeling. So I will have a mask token here. So my tokenizer dot mask token, and you have already seen that what is the output of this particular expression, tokenizer dot mask token. That's this. Okay, so this is the place where I want to do kind of fill in the blanks by this BERT for masked LM model. The opera house in Australia is in, then there's a blank and city. And I also need um, now I'm pretty much invoking the tokenizer dot encode plus, sorry, that's text, and return tensors will be PT for PyTorch. All right. So now in order to get the tensor of softmax values of all the words in BERT's vocabulary for replacing the mask token, we need to specify the masked token index. And this we can get using torch.where. In this particular example, I'm retrieving the top 10 candidate replacement words for the mask tokens. So what I'm going to do, let's do that in the next cell. Torch.where input, to that I will get input IDs 0. That should be equal to tokenizer dot mask token ID. So that's the that's the condition here for torch.where. Now, to know about what I just did, mask token IDs and my previous line over here, where is that? Here, tokenizer.mask token. So let's go to the official documentation of Hugging Face BERT tokenizer. So here it's clearly written, the mask token. This is a special token representing a masked token used by masked language modeling pre-training objectives like BERT, will be associated to self.mask token and self.mask token ID. And now I'm just getting the output from the model. And then the logits from the output. Yeah, that should work. Let's run this. Cool. Okay, so after we pass the input encoding into the BERT model, we get the logits simply by specifying output.logits, which is what we did here. And and after this, we can finally apply a softmax activation function on onto this logits. So my softmax will be f.softmax. We have already imported f, right? Yeah, torch.nn import functional as f, right? f.softmax logits dim will be -1. And So with this line, by applying the softmax onto the output of the BERT, we get probabilistic distribution for each of the words in BERT's vocabulary. So words with a higher probability value will be a better candidate replacement words for the mask token, which is what the purpose of this line. And now, in order to get the tensor of softmax values of all the words in BERT's vocabulary, for replacing the mask token, we can specify the masked token index, which we already have from this line, that is torch.where. So what I'm going to do is mask word will be softmax. From there I get mask index and slice for everything in this dimension. Yep. And after getting this mask word further, because in this particular example I am retrieving the top 10 candidate replacement words for the mask token. So I'm going to use a particular method of PyTorch called torch.topk. So my top 10 will be torch.topk mask word 10 dim equal to 1. From there 1 and 0. And finally, after this, the process becomes relatively simple, as now all we have to do is iterate through the tensor and replace the mask token in the sentence with the candidate token. That is the top 10 tokens which has a top 10 highest probabilities. So let's run this loop for token in top 10. Tokenizer.decode. Now I need to decode it. That's my word, and the new sentence will be tokenizer.mask token. That's what I'm going to replace with the word, and then print the new sentence. Cool. And after running this cell, I am getting the very much expected result. So the very top probability, they are saying the opera house in Australia is in Sydney city. Okay, Sydney, there should be a space between Sydney and city. So let's just change this here. Because after my tokenizer.mask token, I'm just adding a single space. And from here, run it again, run after. Cool. Now it looks better. Yeah. So the first one obviously pretty much gives me the answer, and that's the top probabilistic output from my model. And note that here I actually use a top 10 candidate to replace to get my new sentence, but actually in the practically I just wanted to get the top one, that is the one with the highest probability, which will be my Sydney city. And in that case I don't have to use the storage.topk, because if I just wanted the top very top probabilistic one prediction, then I could have just used something like this. So this would be my softmax, then mask word, and instead of top k, I'll be using the storage.argmax. That will be my top word. But here I use top k to get my top 10 words. So anyway, this solution would have given me the very highest probability prediction from the model, which is Sydney city. All right. Alright, that's what the first part of this video, that is the base use case of BERT, concludes. And now I'm going to check out the next base case application of BERT, which is next sentence prediction. Let's put some text over here. So the next sentence prediction is a task of predicting whether one sentence follows another sentence, and I'm going to use this BERT for next sentence prediction model. It returns logits, which is a prediction scores of the next sequence prediction. So first, as usual, let's bring in my relevant imports. Import BERT tokenizer, which I already have imported earlier, and then BERT for next sentence prediction. Cool. And I already have torch and functional as f imported, so I can directly start with tokenizer. So my BERT tokenizer in this case will be, again, BERT tokenizer dot from pre-trained BERT base and cast model. This time will be this one. And again, from pre-trained cool. And I'm going to use two sentences. One is prompt, another one is next sentence. And then I'm going to encode both of them. So let's actually run this cell and let's see if it's fine. Yeah, it ran fine. And now, okay, sorry, now this. So my two prompts are, actually one is prompt and another one is next sentence. So this is my two inputs. So the prompt is, I came back from office in the evening, and next sentence, I opened my beer after office. And we are going to check if this is a good next sentence for this initial prompt. First, encoding. Encode plus, and I'm going to give prompt, then next sentence, return tensors equal to pt. Oh, I have not. Have I defined a model? Yes, I have. Here is my model for next sentence prediction. Yeah, so I can directly apply the model here to get my outputs. Softmax will be f dot softmax. Just print this softmax. Okay. Cool. Run this cell. All right. So I got these two as my final output. That is the probabilities of the first sentence and the next sentence. So to sum up, these next sentence prediction is a task of predicting how good a sentence is as a next sentence for a given sentence. In this case, prompt variable is the given sentence, and we are trying to predict whether next sentence is indeed the next sentence. And to do this, the BERT tokenizer automatically insert a SCP or separator token in between the sentences, which represent the sep tokens actually represents the separation between the two sentences and the specific BERT. For next sentence prediction model, it predicts two values. That is the final output from these BERT for next sentence prediction will be two values of whether the sentence is the next sentence. And these two values are returned in a tensor the first, and which is what we got, that is this is my tensor. And in this tensor, the first value represents whether the second sentence is a continuation of the first, and the second value represents whether the second sentence is a random sequence or not a good continuation of the first. So unlike masked language modeling, which you did previously, we don't retrieve any logits because we are not trying to compute a softmax on the vocabulary of BERT. We are rather simply trying to compute a softmax on the two values that BERT for next sentence prediction returns, so that we can see which value has the highest probability. And this will represent whether the second sentence is a good next sentence for the first. And here is that tensor for me, and because here we can see that the first value, that is this 9.998e minus 01, this is considerably higher than the second value. So that means BERT believes that the second sentence follows the first sentence. That means, like we said, this represents a probability whether the second sentence is a good continuation of the first sentence. And because this value is so much higher than the next probability, that is the next value, we can very confidently decide that here in this case, this next sentence, that is this I opened my beer after office, is a good continuation of the first sentence. All right, there ends this segment on next sentence prediction, and the next and the last base case use of BERT that I'm going to cover in this video is question answering. And for this, I'm going to use a specific BERT model called BERT for question answering. So let's just import them first from transformer. Tokenizer and BERT for this one, question answering. And from transformers. Okay. And then I need to define my tokenizer just like before. Question names. And inside, I have to pass the pre-trained model name, which in this case is this DeepSeek BERT base cased squad. And my model will be, as you can expect, this dot from pre-trained, and again the same name here. Cool. And now I am just first going to use two simple sentences as example, and then I will use a larger sentence for this question answering. So the mechanism here goes like this, that you will have two set of text. The first set is called the context, and then you also need to pass another text, which is a question. So the model will answer the question based on the context text. So my example text, that is the context text, will be, let's say, this GPT came in 2020, and example question is when did GPT-3 come? And now we can use our tokenizer, that is this one, to automatically generate two sentences by, that is two encoded tokenized sentences by passing these two text into the tokenizer. So what I'm going to do is tokenized inputs will be tokenizer. To that I will pass first, I'm going to pass example question And then the next one will be example text. And return tensors for this case is PT because I'm using PyTorch. Now let's print these tokenized inputs to see what exactly they print. No, I see I have made a small mistake here. The tokenizer that I defined here, this line is wrong. This tokenizer is not an instance of a BERT for question answering, but it will be just the original BERT tokenizer. So this is the correct one. Yeah, a BERT tokenizer dot from pre-trained, then you pass the name of the model. Yeah, now it should work. Let's run this and see. Cool. So this is the output, that is a printed form of these tokenized inputs that I got here. And let's understand what I have here, and then we'll go through one by one each of them. So I have an input IDs here, which is this tensor up to here. And then the next key is token type IDs. And that is a tensor up to this. And the last key in this object, in this dict, I got is attention mask, which is this tensor. So that's the output of from my BERT for question answering, and definitely I recommend you go through their official documentation right here in the Hugging Face official website. That's for BERT question answering, and there all these parameters are detailed. So the input ID is what you got in the output. That's the indices of input sequences tokens in the vocabulary. So this is my input ID. So basically, these are this tensor, that is the input ID tensor. This is a tokenized text. That is my context. And then the next thing is this next key in this dict, that is token type IDs. Another important thing to understand, but to understand these token type IDs, first note that some models in BERT or in Hugging Face in general, or NLP in generally, some models' purpose is to do classification on pairs of sentences or question answering. So these kind of models require two different sequences to be joined in a single input ID entry, which usually is performed with the help of special tokens such as a classifier, that is CLS, and the separator. For example, if for this BERT model that builds two sentences and into a single form like this. So like this. So I have a CLS, then sequence A, then a separator, then another sequence B, and then another separator. So that's how two sentences become one for this kind of model, which require two input sequences. And in this case, the two input sequences were this example text, that is a context text, and the example question. And we used our tokenizer, that is this one, BERT tokenizer, to automatically generate this kind of sentence by passing the two sentences to tokenizer as two arguments. That is this line, tokenizer, and then I pass the first sequence and then the next sequence. All right. So here, those two types of sequences are question and context. And when I get within the attention mask, I got this tensor 1, 1, 1, all these ones. Actually, sorry, I'm not talking about attention mask right now. Yeah, I'm talking about this token type ID. So I got in this tensor all these zeros and the ones. So these token type IDs is also called segment ID in BERT, and they are represented as a binary mask identifying the two types of sequences in the model. And in this case, these two types of sequences are represented as zeros and ones. Here the token type of 0 is for question part, and 1 is for the context part. All right, so that was my BERT for question answering on a single example text, but now I'm going to actually run this on a larger text and then raise a question which should the answer of which is included within my context text, and then BERT will give me the answer. So let's do that. First, I need my question. So the text that I'm going to use for this case is this particular text. So the Vatican Apostolic Library, more commonly called the Vatican Library or simply the VAT, is a library of the Holy See and so on and on. So what I'm going to do is this whole text I'm going to pass as context, and then my question will be to BERT, when was the VAT formally opened? And we can see that already looking at this, that the answer of that question is right here, formerly established in 1475. So let's just do it. So first I'm defining these two variable, text and question. And so this text is this entire, the one that we just saw. It is not getting wrapped in Google Colab. But anyway, and my question is, when was the VAT formally opened? And now I'm going to declare my tokenizer and model just like before. And then let's do a context management here. Torch dot outputs equal to model tokenized inputs. Let me see, tokenized inputs. Oh, sorry, I have to define the tokenized inputs again because that was for a different text previous, for that is a previous example. So let's define my tokenized inputs again. That will be tokenizer. And this tokenizer, we can reuse it again because that was defined already here, and that's just the instance of this BERT tokenizer object. And from pre-trained, deep set, BERT base cased squad 2. That's the name of the model. Yeah, so tokenizer here will be, to the tokenizer, I need to pass the question. And my question here in this case is, when was the VAT formally opened? And then the second is text. And also I need to mention return tensors equal to patim. Cool, that should work. Model tokenized inputs. Okay. And now, okay, now another important concept is called start logits and end logits. Again, you can check the documentation. Basically, start logits is that defines a span where it starts a score before softmax. That is, the answer starts at that span, and end logits is where the answer ends at that span. So it basically gives me the indices where the answer kind of resides. And that's very much the job of the model. That is, I get the start logits and end logits from the output. And basically, the model will tell you at what start and end position of the input IDs the answer to the question will be located. That's kind of the simplest explanation of that. Okay, so you will see my answer start logits will be start index will be, I have to get it from the outputs dot start logits, and I have to apply argmax on that to get the max values. And similarly, my answer end index would be outputs end logits dot argmax. Cool. And now finally, the predict the answer tokens. So predict tokens will be tokenized inputs dot input IDs. How did I get this input IDs? Because you already saw when I printed these tokenized inputs, I got a dict which has 3 parameter or 3 keys. The first one is input IDs, then I have token type IDs, and then lastly I also have attention mask. So I'm just here extracting the value of, grabbing the value of input IDs. And from there, I need to get 0 answer start index, then up to, sorry, that's a slice notation, answer and index plus 1. And finally, to actually see the result, that is, see the answer, I have to decode these predict answer tokens, because this is a tokenized form. I have to decode it to see the actual answer. So tokenizer.decode predict answer tokens. Cool, that should work. I just ran the cell, and that's it. That's my answer, 1475. What exactly we saw in the text, that is, this was my original text, and in the second line it clearly said formally established in 1475, and that's exactly the answer that BERT gave me from my question. So again, this question was, when was the VAT formally opened? And the simple answer to that is 1475. And we got this by decoding the predict answer tokens from this model, that is BERT question answering. And once more again, that all these are very well described in Hugging Face original documentation, official documentation. So this is their documentation. You just go to BERT for question answering, and there you can see all these parameters, what are input IDs, attention mask, token type IDs, etc. So if you go to token type IDs, I think this is the explanation here. It's given that exactly this is the thing that we just discussed. All right. Yeah, you should definitely go through their beautifully written documentation. And as a final point on these BERT question answering, also remember here I applied the model directly, but of course, just like any other Hugging Face model, you can do many fine tuning. Also, you can customize these BERT question answering model to some extent to apply before applying it to your dataset to get better results. All right, that pretty much wraps up this video. If you have liked this one, smash the like button. And also do subscribe, because I'm going to do many interesting NLP projects over the coming days and weeks. So see you in the next one. Thank you very much for watching.